Welcome to week 8. This week we're going to continue talking about linear algebra and vectors. We're going to start by talking about rotation matrices, and then we're going to talk about eigenvalues and eigenvectors. But to start off with, we're going to do a warm-up so you'll remember what we did last week. Okay, so in the first one, just go ahead and write those vectors as matrices. For the second one, calculate the dot product of those two vectors. And for the third one, multiply this matrix times this vector A. So find this product. Alright, pause the video and get warmed up. This first one is quite straightforward. It's really convenient to be able to write vectors this way. Alright, the second one we have to change vector A to a row matrix, and that's called transposing a matrix. And when we do this multiplication, we get minus 10. Alright, I'm not going to work out number 3 because this is warm-up, but I will show you the answer. So you should have gotten that when you multiply this matrix times A, you get A back. So 1 for your x component, 3 for your y component, 4 for your z component. And that is because this matrix C is the identity matrix. It's a special type of matrix. If you want to multiply a matrix times 1, this is what 1 looks like in matrix form. And if you want to do that in 2D, you could probably guess the 2D identity matrix. Just looks like this. It's the diagonal matrix. Okay, now I want to look at some more applications for matrices. And so the next application I'm going to look at is rotation matrices. So this comes in handy anytime you want to represent a vector rotating in physics, which comes up pretty frequently. So in 2D, your rotation matrix looks like this. So let me draw a picture to show you what this matrix does. So if we have some vector in the xy plane, I'll just call it r, and we want to rotate it through some angle theta, and then we want to know what our vector is afterwards, and we'll call that r prime. Multiplying this matrix times your vector is going to get you your new vector. Let me show you an example to make this a little bit more concrete. So I typically work in radians, but sometimes it's nice to also remember what our angles are in degrees. So we want to find A prime. That's our vector after it's been through the rotation. So we need to plug our angle into this rotation matrix. And then we multiply that times the vector A written as a column matrix. So it only has an x component, so it's written like this. Okay, so let's write out. So cosine of pi over 4 and sine of pi over 4 are both the same thing. They're both 1 over the square root of 2. Or the square root of 2 over 2 if you prefer. So if you'll multiply this out, what you'll get is 2 square root of 2 for both your x and your y component. You can rewrite this as a square root of 2 and a square root of 2. That's just some algebra. Okay, so I picked a simple example so it'd be easy to draw the picture and see what's happening. Sorry, all my lines keep coming out crooked today. Okay, so our initial vector is 2x hat, so that's over here. So that's A. Then we rotate it 45 degrees. And so here's our new vector, A prime. So this vector is still too long because this is the square root of 2 and this is the square root of 2. So this is 2. But now it's rotated 45 degrees. So basically what the rotation matrix does is it saves you from having to do complex geometry, because in general this problem could be some pretty tough geometry, but now the rotation matrix is taking care of all of that for you. So this maintained its length, but the direction changed, just like it was supposed to. Now in 3D, this gets a little bit more complicated. In 3D, we have a different rotation matrix depending on what our axis of rotation is. So if we're rotating around the x-axis, you always want to be careful that you put your negative signs in the right place. That's an easy thing to mix up. Alright, if you're going around the y-axis, and then there's one for going around the z-axis. So what you can see is that we have the 2D rotation matrix in part of it, and then we have the identity matrix in the part for the axis of rotation. So the part of your vector that's along the axis of rotation isn't going to change, but the other parts of your vector are going to change. Another thing to be careful of is when you're rotating around the y-axis, the negative sign that goes on your sign is in a different position than for x and z. And if you just try this out for a few examples, you can see that that needs to be the case, but it's an easy place to make a mistake. Let's look at an example. So we're going to do something kind of simple again, just to see that it works. And we're using trig a lot again, so I hope you remember your unit circles. Okay, so basically to find b prime after we rotate it, we need to fill out our rotation matrix for around the x-axis. And then multiply that times our vector b, written as column matrix. And it just has a y component. So cosine of pi over 2 is 0, sine of pi over 2 is 1. Lots of zeros in this multiplication. So what you'll get if you work this out is 3z hat. So let's draw out a picture of this so we can show ourselves that this worked the way it was supposed to. So I'm going to draw my 3D axes here. And conventionally, this is how I draw my axes in 3D, is that the x is over here, y is over here, and z goes over here. So we're starting out with one that's purely in the y direction. 1, 2, 3 over here. So this is b. I'm rotating it 90 degrees about the x-axis, which means we're rotating this way. 90 degrees means we go all the way to the z-axis. So we end up with 1, 2, 3 over here. So we should be 3z hat. So again, I picked a simple example just so that we can see that this works, but in general it will work even in situations where it will be really hard to see what you should end up with. Okay, I'm going to give you 2 examples to try out yourself. We're getting a little bit more complicated here, but not too terribly complicated. I like to use angles that you can get out of the unit circle so that you don't have to use your calculator. Alright, go ahead, pause the video, and give these a try. So we are looking for C prime. So we need the rotation matrix for the z-axis, and we need to plug in pi over 2 for our angle. Then we need to write our vector c as a matrix, so that's 1, 1, 0. And remember, cosine of pi over 2 is 0 and sine of pi over 2 is 1. So if we multiply all of this out, we end up with minus 1, 1, 0, which is minus x hat plus y hat. And when you're doing this sort of thing on your homework, you can leave your answer as a column matrix, that's fine, or you can write it in component form. It's a matter of personal preference, they both represent the same thing, unless I specifically tell you otherwise. Let's look at a picture of this, since this one isn't too bad to look at. So if you draw x and y conventionally like this, then the z-axis is coming out of the page. So we start out with a vector that's over here, x hat plus y hat goes over here because this x component is 1 and this y component is 1. We end up with a vector with an x component of minus 1 and a y component plus 1. So we end up over here. This angle is 90 degrees. So you can see that works out correctly. Let me know if you want me to talk more about how we draw our axis in 3D. We will definitely be talking about it more next week as we go into vector calculus. Okay, let's look at our next one. Now our next one is getting a little messier, so I wouldn't really recommend drawing pictures for it, at least for me. If you are especially talented at drawing 3D pictures, you can give it a try. Alright, so we need the rotation matrix around the x direction. And again, just be careful where you're putting your negative sign in your rotation matrix. It's really easy to get mixed up, especially when you're rotating around y. Alright, so this vector is 2, 4, 6. Cosine of pi over 6 is the square root of 3 over 2. The sine of pi over 6 is 1/2. So if we work all that out, we get, which you could also write out in component form. Although it looks a bit messy. Alright, I'm not going to draw this out because I cannot draw this clearly, especially without graph paper. But what I want to point out is that the x component didn't change. So you were rotating about the x-axis, which means only the y and z components are going to change. But the x component stays the same. Let me know if that makes sense to you. And you can write matrices that represent all sorts of rotations or transformations. You could have rotations that are about axes other than x, y, or z. You could do flipping like a mirror. You can write transformations as stretch vectors. Your book talks about it more, but due to our limited time, I'm going to go into using matrix transformations in much more detail than this. Alright, so the next thing I want to talk about are eigenvalues and eigenvectors. This is a concept that at first seems pretty abstract, but they're very useful in physics, especially in quantum mechanics. And if you've already taken quantum mechanics, then I think this will seem a little bit familiar to you. We were just talking about rotation matrices and other transformation matrices. So eigenvectors are special vectors whose direction is not changed by that matrix transformation. And eigenvalues are the amount by which the vector is scaled. It can also take on a negative value so that the vector could flip 180 degrees, and that would still qualify. I think that sentence is a little bit hard to follow, so I think it's better if I write this out as an equation and do some examples. So we're multiplying our matrix times some vector. And after we get that, what we're really going to get is just our vector scaled by some value, lambda. That lambda is our eigenvalue. It's just a number. The matrix has, like if it's a 2 by 2 matrix, it has 2 eigenvalues and 2 eigenvectors. So for a 2 by 2 matrix, there will be 2 of these special eigenvectors where you could write this equation. And we want to find out what those vectors are, and we want to find out what the eigenvalues that go to them are. So we can rearrange this a little. And I'm writing m minus lambda 1. This 1, I mean the identity matrix. So let me write that out for a 2 by 2. So we're looking for the vectors that will satisfy this condition and the values of lambda that go with it. I'm betting this still seems pretty abstract. Let's look at an example. So when we want to solve for eigenvalues and eigenvectors, we start off with some matrix. All of these questions will say, here's a matrix, find the eigenvalues, and find the eigenvectors. So the first thing we want to do is find the eigenvalues. So the way that we do that is we use the determinant. So we write 2 minus lambda minus 1. So we're looking for when this determinant equals 0. And basically that comes from this equation. If the determinant of this equals 0, this equation will be true. So this is our matrix with minus lambda on the diagonals. Okay, so we need to calculate our determinant. So that's 2 minus lambda. minus 6 minus lambda minus 7. So we can do our algebra, multiply this all out. And it's nice when it works out that you can factor these, but you know, if you have trouble factoring these, or if you just get a question where the factoring doesn't work, you can always use the quadratic equation instead of doing this. So we get lambda can be minus 5 or 1, and these are your eigenvalues. Alright, so because of this equation, we need to find the determinant of this matrix when this determinant is 0. And that lets us solve for the eigenvalues. Alright, now that we have the eigenvalues, we can go on and find the eigenvectors. So that requires going back to our original equation. So each eigenvalue corresponds to one eigenvector. There are exceptions, but we're not going to worry about that right now. So one of our eigenvectors is 1. So for something to be an eigenvector, it has to be true that we can take the matrix, multiply it times that vector, and we will get that vector scaled by the eigenvalue. So here our eigenvalue is 1, and we just multiply it times that vector. So we can write out what these equations give us. So here we're doing our multiplication. So we get 2x plus 7y equals x. And we get minus x minus 6y equals y. Both of these equations are the same thing. If we do a little bit of rearranging for each of these, this one turns into x plus 7y equals 0, and this one gives us minus x minus 7y equals 0. So both of these equations give us the fact that x equals minus 7y. So you don't actually have to do both of these equations because they're going to tell you the same thing, but if you want to make sure that your eigenvalue is correct, you can go ahead and run this and make sure they both give you the same thing. So basically this just tells us that whatever y is, x has to be minus 7 times it. There's always going to be an arbitrary scaling factor. Technically, you could say that your answer is minus 49 and 7. Unless I ask you to normalize, that is change the length of your vector to 1, you can pick whatever you want. And at this point, I'm not making you normalize. But if you were doing quantum mechanics, then you are going to normalize. Now for our next eigenvalue, we have lambda equals minus 5. So we're still setting up the same thing, but now instead of 1 being our scaling factor, minus 5 is our scaling factor. So if we multiply that out, this is what we get from the top row. The bottom row is going to give us the same thing, so I'm not going to bother to use it. But again, you can always use it to check yourself if you want to. So this gives us that 7x plus 7y equals 0. So we know that x equals minus y. So just pick a value for x or y and make the other one match. So I'll just make y to be 1, that's the easiest thing normally to do, and I'll make x equal minus 1. And this is for lambda equals minus 5. So when writing down your eigenvalues and eigenvectors, you always want to specify which eigenvector goes to which eigenvalue. They are not interchangeable. And we'll get to an example in a little bit where this has some physical meaning. And it always has some physical meaning if you actually know what the transformation is, but we're going to do a spring problem in a little bit. But before we get there, I want you to try one out for yourself. Alright, so I gave you the matrix. I want you to find its eigenvalues and eigenvectors. And since it's a 2 by 2, that means there's 2 eigenvalues and 2 eigenvectors. Pause the video and give it a try. So first, we want to find the eigenvalues. Okay, so the eigenvalues are 4 and minus 1. Then we want to find the eigenvectors. So this tells us that x and y should be the same, so our eigenvector is 1, 1, or 2, 2, or 500, 500. It doesn't matter. Okay, that's for lambda equals 4. Ooh, that's a woo-woo line. Okay, now I want to do lambda equals minus 1. So this tells us that x equals minus 3 halves y. So my default method is to write minus 3 halves 1. But I like to avoid fractions, so I might write that as minus 3, 2. Or you could even write 3 minus 2. Those all work. I know this all still seems pretty abstract. This is going to come in really useful when you're learning quantum. So when you're doing quantum, eigenvectors or eigenfunctions will represent the quantum states. And you'll be able to write any state as a sum of eigenvectors. So basically any arbitrary vector can be written as a sum of those eigenvectors. They're basis vectors if you are familiar with that concept. And eigenvalues are the values you actually measure in quantum, like energy. But we're going to do an example using a spring now. Okay, so the main thing I want you to get out of this is what the physical meaning of eigenvalues and eigenvectors can be. So let's look at our actual example. So what we have is 2 masses and 3 springs. And we're going to call the position of mass 1 x and the position of mass 2 y. We're going to say all the masses are identical, and we're going to say that each of the spring constants is k for all 3 of the springs. So the first thing we want to find out is what are the forces on each of these masses. So recall the one that's represented by position x, we'll call that mass 1. So what are the forces on mass 1? The force from this spring is just minus kx, standard Hooke's law. But the force from this spring over here on this mass is going to go in the other direction. And it depends on the distance between y and x. So that looks a little bit more complicated. But we can simplify this. Now to find the forces on the second mass, well, on the left we have this spring, which the force from that spring depends on the distance between y and x. And then the force from this spring just depends on y. So if you look at the signs, I'm putting the negative sign when the spring is on the left side, and I'm putting the positive sign when the spring is on the right side. Now if we clean that up, we get kx minus 2ky. And if you're having trouble following what the signs should be, and using Hooke's law in this context, which is more complicated than what we normally do, then I encourage you to pause the video and think about it for a few minutes, or go talk about it in the problem-solving discussion. Make sure you understand where these equations come from. The next thing we're going to do is go back to Newton's second law. So this first force equation is equal to mass times the acceleration in terms of x, and our second one is our acceleration in terms of y. And remember, acceleration is the second derivative with respect to time. So we get 2 differential equations out of this. So our first force equals this derivative, and our second force equals this derivative. Okay, so this is our system of coupled differential equations. Alright, now we're going to do something that looks like a bunch of cleverness, and I wouldn't expect you to be able to figure out immediately on your own. But I think it'll generally make sense to you. So basically we want to solve that system of coupled differential equations. And because it springs, we can assume our answer is in some form of oscillations. So we would say that our solution for x is 8e to the I omega t. Seems like a reasonable thing to say. And similarly for y of t, that it would also be of that form. Okay, so we want to basically plug this back into our equations. So the first thing we need to do is take our second derivative, which you've done lots of times and with this form, so I'm not going to show you every single step. But feel free to pause the video if you want to work this out for yourself. I do encourage that. And another way you can write this is basically you just get minus omega squared x back here, and you get minus omega squared y here. Which, if you remember solving our differential equations of the form d squared x dt squared equals minus omega squared x, which we did a couple weeks ago, and it should look familiar that this works out this way. So then basically we want to substitute this for this in our differential equations, and substitute this for this in our differential equations. So what we get when we do that is this. Now I'm going to rearrange this a little bit. Alright, so I just divided through by k on both sides. So if you remember previously we had found that we had defined omega to be k over m, the spring constant divided by the mass, square rooted. But right now we don't know what omega is. We need to solve for omega. So we're going to rewrite this equation. Remember when we had a system of equations for calculating how rays changed in an optical system, we wrote the equation as a matrix. If you look at this, you can see we can do the same thing. So now we have minus 2 and 1 up here, 1 and minus 2 down here, multiplied by xy equals minus m omega squared over k xy. And you can do this matrix multiplication and verify that this is true if you can't quite see that right away. As you work with matrix multiplication more, it'll become more clear that you can do this. But really, I encourage you to just work it out if it's not obvious to you right away. So I hope you see that now that I've rewritten the equation this way, that what we have is an eigenvalue-eigenvector problem. This is our eigenvalue. Xy is our eigenvector. We don't know what that is either. So we have lambda equals minus m omega squared over k. So by solving this as an eigenvalue equation, we can find out what the frequencies are. So I'm going to have you do that yourself. So remember, your matrix, this is what your matrix is. So go ahead and find your eigenvalues. Pause the video and hit play again when you're ready to continue. Let's work this out. Okay, I didn't do this on my head. I'm just trusting that you can figure this out yourself. The next thing I want you to do is use the eigenvalues to solve for omega. Alright, pause the video and work that out. Okay, this requires some algebraic manipulation. So omega is the square root minus lambda k over m. So one of your omegas is the square root of k over m, and the other one is the square root of 3k over m. So these are the frequencies of the normal modes of vibration. We'll come back to talking about what that means in just a few minutes. But before we do that, I want you to find the eigenvectors. So when you're finding the eigenvectors, remember minus 1 and minus 3 are your eigenvectors, not the frequencies themselves. Alright, pause the video and work it out. Alright, so for lambda equals -1, we get that y equals x. This means that our eigenvector is 1, 1. For our other eigenvector, we get that y equals -x, or -1, 1. But what does this mean? Okay, so when you have a system of springs like this, we have what are called normal modes. So these are the modes of vibration that every complicated vibration can be written as a sum of. So if you have your spring vibrating such that your eigenvector is 1, 1, that means x equals y. That means when the first mass moves to the right, so does the second mass. When the first right moves to the left, the second mass is moving to the left. So they're vibrating together, and when that's the case, their frequency of vibration is just the square root of k over m. What the second mode is that it says y is always -x. So that means when the first mass moves to the right, the second mass moves to the left, and vice versa. So they're out of phase. When they're vibrating like that, then their frequency is the square root of 3k over m. And it can be a complicated vibration, but these are the two modes it's made of. That's what it means for them to be eigenvectors, that they're basis vectors, that any vibration can be written as a sum of the other two. And this is something that's very abstract and hard to grasp at first, but the more you work with it, the more familiar it will seem. So this is important when you're talking about masses on springs, and we talk about masses on springs in large part because that's how we model waves, and waves are very important in nature. And it's also extremely important in quantum mechanics. Okay, let me know if you have any questions. Also, you can read more about this in the textbook. Alright, hope to hear from you soon. See you next week.